Now let's do a numerical example using matrices and vectors. So let us go directly into this example and solve it. You will see it is much more easier, and it takes less time to solve the examples using matrices as compared to the scalar case. In scalar case we had 2 neurons, but there was still a lot of mathematics involved, and now I have increased the number of neurons and also the input from constant to variable. This is the same function which we want to approximate using neural networks. So instead of constant inputs, now I am assuming some nonlinear inputs. So let's go directly into solving this using neural networks. So the first thing is that we want to write the input matrix X. So we know this, that it can be written like this, okay, and which is equal to sine of t and cos 2 of t, right? Cos 2t, this is inside the angle, this t is not outside this function, okay? So let's say we are doing it for the time 0.5, okay? So what will be the x vector? We will simply substitute 0.5 here. Take notes of this. This is radians, okay, and this will be cos 2 times of 0.5. So x vector will be, I have already derived these matrices. I may have made some mistakes, so please verify the mathematics with you. But meanwhile I have already derived this, so I will be writing these matrices quickly instead of doing all the mathematics in calculators and everything. So what will be the x vector after substituting the values? It will be 0.4794, 0.5403. So this is my x vector. Okay, now we have learned this, that we have to do the linear combination. All the steps will be same. We have to do linear combination, right? I will assume b equal to 0 to make it simple and solve this numerical example quickly, but you can choose some values for this and it will not change much. So the first step is always to do linear combination, then activation, right? Then derive y hat equal to v transpose into activation. In some cases I wrote this as h, so it is both are same, because h or this sigma, these are actually activations. After that we derive error, which is y minus y hat. So let's find this y as well. So when I substitute these x values, x1 and x2, this is x1 and this is x2. So what will be the value of y? It will be 0.4794 square plus 0.5 times 0.403. okay, this is obtained from here, and this is x1. So coincidentally this becomes 0.50. I don't know why it become this, but I had no idea, but coincidentally y is equal to 0.50. okay, so we will be using this y and estimating y hats. I will perform 2 iterations, by the way, to see how this error changes. Once we obtain e, after that we have to find dj by dv, which results into v nu, and after that dj by dw, which gives us w nu, right? Once we obtain these values, v and w, we will use these in the first step. Sorry, this will be w nu, and this v nu is used in this third step. So it will be like updated after each iteration. So I already have x vector, so now let's proceed with the first step. where we will derive the linear combination. So linear combination is given by z is equal to w. This is the first step, times x. I told you b is equal to 0. I assume this. You can also take some value for this as well. So I have x. What is my w matrix? So w, actually we know this, we saw this in the previous video. Its dimension are like this. N is number of neurons and the small n is number of inputs, right? So w will be a 3x2 matrix. So let me write it here. This will be a 3x2 matrix. We will have some elements over here. So how we determine these elements? So to begin our neural network, the values of w and value of v, these are the value we have to initialize in the beginning. Let's go back to the previous slide. Wait, I don't know why I'm unable to go to the previous slide, but anyways, let me draw it here. Let me draw it quickly over here. We have a neural network like this, right? And this is connected over here. So we can see we have 6 weights here: W12, W21, W31, and so on. And similarly, we have this V1, V2, V3. Okay, so in the beginning, we have to initialize these values. So we have to choose these values randomly, right? So I will choose some values. Let me choose this as a 0.5, this as -1, this as 1, 0.5, this is 0.5 again, and this is 1. So okay, let me explain this to you, why this is 3 by 2. If you recall, we had z1 is equal to w11x1 plus w12x2. This was for the 2 neuron case, w21x1 plus w22x2. So now we have 3 neurons, so this becomes w3 is equal to w31x1 plus w32x2. So we can see here we have these. This is already visible to us. So these values actually we need to initialize, right? So I chose these values randomly. Okay, so what happens after this is that we obtain z is equal to 0.5, not this, -1, 1, 0.5, 0.51, and I have x vector which I calculated earlier, which will be constant throughout the neural network. Our only updates will be w and v, and if in case we are using bias with input and b bar with the output, so these values will change. But for this example, I am assuming these values as 0 to solve this numerical example quickly. So what was the value of x? Let me see. Yeah, so we already saw this in the previous slide. This is the value of x. Just to see the dimensions, so this is 3x2, right? And this is 2x1. So the matrix multiplication is compatible, and we will obtain z equal to, z will be a vector with the values equal to, I need to see this, yeah, minus 0.3006, 0.7495, and this will be 0.3006. okay, we know this multiplication, right? 0.5 times this plus then -1 times this, so we will obtain this value. Similarly for the second row we will get this value, and then for the third row. But please verify these values. I may have made some mistake over here, so I'm not sure about this. Actually, I am sure I already made these notes, but I may have made a mistake. So please verify these values using calculators, or if you are using MATLAB. Okay, so the first step is to do the linear combination, which we have already done here. For scalar case, we were doing this separately. First we used to calculate z1, then h1, right, then y hat. After that, y hat. After that, perform this again. So it took a lot more time than this. And here, in just one step, z is equal to wx, we derive the value of all three linear combinations. So now the next step is to do the activation, which is really easy because we already know this. How to do activation? Activation, we have to pass this vector z through a sigmoid function, right? So if z is 3 cross 1, this will also be a 3 cross 1 vector. I already calculated this, so this will be 0.4254, 0.6791, and 0.746. Okay, so this is the second step. How do we calculate this? Just to give you some just to give you the method. So we had z1, right? There was some value for z2, and right, and these values are obtained from the vector z, which we calculated previously. Now the next step is to do the final estimation. So we know this, right? Very easy. Now this is V transpose. Let us assume that previously I assumed these two values. Let me add a third one, because now we have 3 neurons. So if you look at the output layer, previously we had 2 neurons, so it was V1, V2. Now we have 3 neurons, so there will also be a V3. So I assume this as 0.5. And previously I had assumed V1 is equal to 1, V2 is equal to -1. And don't forget this transpose. If you forget this, we will not be able to do the multiplication. And this is sigma z. So when I write this without transpose, or you can say when I apply transpose to this, so this column matrix will become a row matrix, and sigma z, which is activation, so we can obtain from here 0.4254, 0.6791, 0.5746. Okay, so what we will get is that the value of y hat, so y hat will be equal to, I have already derived this, just let me see here. Yes, y hat will be equal to 0.0336. Okay, now what is our next step? So next step is to do the difference between real and estimated function. So e is equal to y minus y hat, right? What was the value of y? We already calculated this. It was 0.5. This is 0.0336. So e is equal to 0.4664. Please verify this. Okay, please verify this. I may have made a mistake while using calculator. Okay, so now we have e. So after that, what we did previously, we used a loss function and then derived dj by dv and dj by dw. Now we don't have to go in this mathematics because we already know the formulas of dj by dv and dj by dw. So we will directly use these values to find the gradients So let me do that. If you recall, or if you can see your notes, so we calculated the value of dj by dv, not value, we found this formula for dj by dv equal to minus e times h. So this is actually activation, right? So let me put the values here. So this is minus, what was the value of e? 0.4664, I think, and the sigmoid was 0.4254, 0.6791, 0.5746. Okay, so dj by dv becomes minus 0.1984. Please verify these values. I may have made a mistake. I'm just recalling and just informing you about this, because there is a lot of mathematics involved. But the good thing is that mathematics is only about multiplication, addition, subtraction, nothing much, because we know these formulas already, so we don't need to go into its detail. Now we have dj by dv. Next step is to derive dj by dw. So if you have noted down its formula was minus e times v times, but this was special multiplication, if you remember, sigmoid of z. I will tell you again, just wait a moment. And this was x transpose. For these three, we had a special multiplication, that was that we have to do element wise multiplication. If we don't do element wise multiplication, then we will not be able to match the dimensions of left hand side, right? So let's call this as q, or any variable you want to call it. So let's calculate q first of all. Element wise multiplication of sigmoid, and then element wise multiplication of its difference from 1. So this becomes, I assume this v, we initialized this, right? We initialized w and v. So this is actually 1 minus 1 and 0.5. Then element wise multiplication, this is 0.4254, 0.6791. We can also see it from here, okay, 0.5746, and this same value but subtracted from 1. Okay, so 1 minus 1 minus 1 minus this. I will just save our time, so I will put arrows over here. So same values but 1 minus sigma of z. So when we solve this, what does it mean to do the multiplication element wise? So this is the first row, right? So we have to do 1 times 0.4254 and then 1 minus 0.4254. This is not traditional matrix multiplication. So each row will rows element will be multiplied with each other. So we will get q equal to a row vector. Why we have to do element wise multiplication? Because this v is 3 cross 1, then this is also 3 cross 1, and this is also 3 cross 1. So this multiplication is not compatible if we follow the rules of matrices, because this one is not equal to this 3, right? For matrix multiplication, if they have to be compatible, both of these should be same. So after solving this element wise multiplication, we get the value of q equal to 0.2444 minus 0.2181, 0.1. Okay, now we can derive the value of dj by dw, which is equal to minus e. So what was the value of e? 0.1984. 4664, right? Now this is Q, so this matrix will appear here as it is, times X transpose. So we calculated the value of X vector, right? There were two elements, but now we have transpose over here. If you look closely in this top right corner, so this will be transpose. So the values are 0.4794, and the second element is 0.5403. So after solving this, what we will get is the value of dj by dw, and it will be a matrix because the dimension of w are n cross small n, 3 cross 2. So once you solve this, let me explain it to you in the next slide. I will explain the slides to you. So now what we are left with is that I want to explain slide and these dimensions to you. Minus E times Q X transpose. So E is actually a real number, so it doesn't have much of effect. Q was 3 cross 1, and X is 2 cross 1, but since we are talking about X transpose, so it will be 1 cross 2. So you can clearly see that matrix multiplication is also compatible here. We can perform this multiplication, and end result will be 1 cross 1 times 3 cross 2, which will be 3 cross 2. This is just the explanation of dimensions. If we solve, when we solve the matrices, which I wrote in the previous slide, we will get the value of this gradient as 3 by 2 matrix. So the value is, let me see from my notes, minus 0.0547, minus 0.0617, then this one is 0.0489, this element is 0.0551, and this element is minus 0.0274, and this element is minus 0.0309. Okay, so we have performed all the computations, but now comes the key point of this all of this discussion. If you remember, we have to update our weights using this law. Okay, so now we have, and for output weight, so now we have all the values on the right hand side. I initialized these values in the beginning, right? Eta, this is our choice, so let's choose 0.1, and I have calculated this matrix and this as well. Sorry, this is not dw, this should be dv, this should be dv. Okay, so what will be the value of, let's do this for w nu. So I chose this value for w nu. What was the initialized value? 0.5 minus 1, 1, 0.5, 0.51 minus eta. We can tune any value for this. I always suggest to start from 0.1. And then what is dj by dw? So this matrix will be here. Okay, so we will get w nu equal to 0.5055 minus 0.9938, 0.9951, 0.4945 minus 0.4973, 1.0311. Now you have to note this value because all of this mathematics is actually for this value of w nu and after that we have to find the value of, this is the W new. Now we have to find the value of V new, and we will have completed the first iteration. So let's go and derive this V new. V new is actually really easy, same as before. V new is equal to, what was the value of V? 1 minus 1, 0.5. What is eta? We have to choose this by ourselves. And what was this dj by dv? This was minus 0.1984, minus 0.1984, minus 0.3167, and minus 0.2681. So we get the value of new output weights as 1.0198. Please verify this if it is 1 or 0, but I think it's 1.0198, minus 0.9683, 0.5268. So we have completed our we have computed values for the input weights as well as the output weights. So now actually what happens? We have to perform all of this computation again, because first iteration is complete. Now we will do the second iteration. But how will we do the second iteration? We will do z is equal to W new times x. Okay, so this is really key point here. W new, this is not multiplication, this is the x vector. Okay, this is a multiplication over here. So this is actually the neural network which we have derived here, and we have updated the weights. So let me call this as a second iteration. With previous one you can write like this, z1, and then we did activation, so h1. This represents the iteration number. Okay, so what will be the value? Okay, after this what we have to do, we have to find same steps, right? We don't have to get confused in these notations. Okay, same steps. First one is linear combination, second is activation. So let me do the linear combination over here. So iteration number 2, linear combination. So what is my value for W new? So this is 0.5055 minus 0.9938, 0.9951, 0.4945, minus 0.4973, 1.031. So this is the new weight. Okay, now we are not using the one which we initialized in the beginning. And x, the value of x will be constant because it is an input, it does not change. So the value of x is actually, let me see here. Okay, I have not substituted this here, but we need to see our notes. Let me see how. Okay, it will be same as before, 0.4794, 0.5403. Okay, so z in the second iteration will be a vector, and it will be minus 0.2938, 0.7441, 0.3037. Once we have obtained linear combination, second step is activation. So sigmoid of z, but of second, this one, recent one. So I will directly write the result over here. Okay, this will be 0.4270, this will be 0.6780, and this will be 0.5753. And then the third step, y hat is equal to v transpose sigma z2. The z2 represent the second iteration, recent values. And now note this v transpose will also be the new one, okay, which we calculated over here. So what we will get is a new value for estimated function. This will be 0.0784. okay, and after that all the steps are same, nothing changes. Now we are only in doing the second iteration. So after that, what we have to do, we have to find the value of error. So error is y minus y hat. This is 0.5 minus, so the new value of y hat will be second iteration. So this will be 0.0784. so E is equal to 0.4216. This is for the second iteration. I just forgot this notation, but I think you can understand what I mean. So previously when we calculated E, its value was 0.4664, and now when we have calculated this E in second iteration, 0.4216, so we can already see the value is reduced, it is converging towards 0, right? So we have to do all these iterations again and again and again, update the values of W, and similarly update the value of nu, and then use these values in linear combination, and then perform activation. And when we derive y hat, we have to use v nu. This will be for the third iteration, right? So and then derive dj by dv, dj by dw. The thing is, we have to perform these computations again and again until we reach a certain value. We can define, like, let's suppose E approaches to 0.001, and then we can tell our simulation to stop, right? And when error approaches here, then it means that y hat will be almost same as y function. Okay, so any other important key point? Yeah, so when we get that, so that will be our end result. So yes, I forgot to mention this. You saw here that we had the value E equal to 0.4664. In second iteration, this is 0.4216. The thing I wanted to mention is that when we were doing example for 2 inputs, 2 neurons, and 1 output, our error was, I think, 1.0 something. So the error was much larger. So when we increased the number of neurons from 2 to 3, we already saw that it was reduced to 0.466. In the second iteration, it reduced further. Yes, we can say that here the inputs are also changed, because now we have inputs equal to sine t cos 2t. Yes, we have changed the input. But the thing is, when we increase number of neurons, the estimation gets better. But there is one concept of PE, persistent excitation, or something like that. So when we increase number of neurons from that threshold, the estimation actually doesn't work. So that is for like higher level classes or something. I just wanted to keep this course for the beginners. So just remember that when we increase number of neurons, our estimation and approximation will improve. So you can perform the third iteration and you will see this error will decrease even further from 0.42. So that's all for this video. I hope it helps. Thank you.